Alright, so what do we mean by buffer capacity? What do you got here?
The amount of acid or base a buffer will accept before it changes the pH.
Anybody want to modify that a little bit?
It's the amount of acid or base it can contain without significant change.
I like if you add significant to your change in pH, that's good because any addition is going to change the pH a little bit. That's bad color. One addition to this, do these have to be the same?
Do the acid or base?
Can a buffer more on the base side than on the acid side? Is that possible?
Depending on how you make it. Maybe?
Okay. So when we're doing the buffer equation, so we'll do like pH is equal to 6.35 for carbonic acid plus log of, I don't know, 2 molar divided by 1 molar. So this buffer can buffer more against what? Acid or base? Acids.
Bases?
It can buffer more against acids, and you know that because this right here is the base. And this right here is the acid part of the buffer. So this particular buffer can buffer against an acid twice as much acid can be added before we get that significant change in pH. Does that make sense?
Mm-hmm.
So if you're more concerned about the acid than the base, then you would add more of the salt of the weak acid to the solution to make your buffer. All right, you're titrating an unknown weak acid with KOH. You've added 35 milliliters of the acid to the formula, and your titration uses 62 milliliters of what's the concentration? All right, so this one's easy. It's concentration of the acid times volume of the acid is equal to concentration of the base times volume of the base. So the only thing that we don't know is the concentration of the acid. So concentration of my base is 1.1 molar. Volume on my base is 62 milliliters, and the volume of my acid we added was 35 milliliters. So those cancel out, and what is this? 1.1 times
2.94
divided by 35. I got how many sig figs? 2. So I'm getting 1.9 molar. Draw any titration curve and label the parts. Okay, so pH is on the y-axis and volume. Titrant is on the x-axis, and if we're going to do, let's do this guy up here. So it's going to be, this is going to be somewhere near 14, and this is going to be, what should I put right here?
Where?
Right here.
I need glasses.
Equivalence point.
Say again?
The equivalence point?
That's what it's called, but what number should I put there?
Seven.
You need to put a number greater than 7. Anybody want to tell me why? This is an unknown weak acid. So that means when my potassium hydroxide concentration equals, we'll just say this is my acetic acid. They cancel each other out. Now I'm at the equivalence point. But what I have now is water molecules and CH3COOKs. So what's going to happen here? The K is not really attached, right? Because it's potassium. And so what's left behind in the water is some water, a spectator ion, and CH3COO negative, which is going to do what?
Make the solution more acidic.
Then I wouldn't have put greater than 7.
Oh, then make the solution more basic.
Because it's going to attack water molecules that are in solution, turn itself back into acetic acid, and leave behind OH groups. So if I'm titrating a weak acid, the equivalence point is going to be above 7. If I'm titrating a strong acid, it's going to be at 7. Does that make sense? What's the pH? Adding 25 milliliters of 2.5 molar to pure water. Okay, so we need to do 2.5 moles per liter, and we've got 0.025 liters. So 2.5 times 0.025, and this is 0.625 moles of OH, and it's just OH because the potassium comes off because this is a strong base. So if
I got 0.0625. Wouldn't it be 0.0625?
Yeah, my bad. There's a 0 here. And then I'm going to divide this by half a liter. Divided by 0.5. So then this is going to be 0.125 molar OH. And if I take the negative log of this, ooh, I get 0.9. So then this is my POH. So then my pH is equal to 13.1. So a massive change in concentration. So we're going to do the same thing, but this time we're going to do it to a buffered solution. So I need to know all of my little pieces here. So I've got 0.22 moles per liter, and this is 0.475 liters, and then I've got 2.25 moles per liter, and that's 0.475 liters. And then we have this number of moles from the problem above. So then I'm going to make a HA A negative ice table. I guess I should do the math on those first. 0.22 times 0.475. So this one is 0.1045 mole. And then we've got 2.25 times 0.475. And this one is 1.069. All right, so then let's see. This is 1.069, right? And this one here is 0.1045. And what is this sodium hydroxide going to react with, or potassium hydroxide going to react with?
KOH. Or no, sorry. It would react with the acid.
Yep, because it's going to make water in the base. So then I'm going to add 0.0625 here. I'm going to subtract 0.0625 here. Okay, so 1.069 plus 0.0675. Sorry, 25. So this becomes 1.1315 and then 0.1045 minus 0.0625. This one becomes 0.042. All right, so pH is equal to plus log 1.1315 divided by 0.042. Somebody have the
Yeah, it's 3.14.
3.14. Okay, so 3.14 plus log 1.1315 divided by 0.042 close parentheses equals, and so 4.57. We needed to do the initial, and we've skipped that question. So pH is equal to 3.14 plus log of 0.22, 2.25. Huh? 4.15.
How did you figure out the initial pH?
I put the concentration of the salt in the numerator and the concentration of the acid in the denominator, took the log of that and added it to the pKa.
And you got 4.1?
Yeah.
So you did 3.14 plus log of 0.22.
No,
Over-
2.25 divided by 0.22.
Oh, I switched them. Okay.
Oh, cool. We got another buffer problem. Can I make this longer? Oh, it just stretches it out. It makes it look weird. Huh. Okay, so let's figure out what the pH of this buffer is first. pH is equal to lactic. Do you have a? Let's go over there. Go here, here, acid base. All right, so lactic acid 3.08. So 0.035 and 12.5. Wow, that's really concentrated. Oh yeah, I put this one on here because Allison wanted another problem. So initially the pH is 5.63, and now we're going to figure out what happens during the course of this reaction. So I've got 0.035 moles divided by liters, and then this is 0.75 liters, and I've got 12.5 moles divided by liters, 0.75 liters, and we've got 2.5 moles per liter times 0.0125 liters. All right, so 0.035 times 0.75, 0.02625, and then 12.5 times 0.75. 9.375.
Wouldn't it be 0.045 for the liters on the base? Because we have 45 milliliters of 2.5 molar LiOH.
Yeah, I don't know why I wrote that. That's strange.
I was like looking around and I was like, where did that number come from?
Nowhere important. 0.045. All right, so 2.5 times 0.045. And so then this one is 0.1125. And what is this? Oh, yeah, I forgot I did this. Okay, so HA, and then A negative, and then ice. And this one is 0.026525. And this one is 9.375. And what's this lithium hydroxide going to react with?
The acid.
The acid. So I'm going to lose this. And I've got 0.1125 here. And over here I've got plus 1.225. But what's the problem?
It's going to be a negative. The HA, it's going to turn out to be a
You
negative.
you can't negative log a negative number, otherwise it's imaginary.
We like imaginary. This ends up leaving us. This ends up leaving us with 0.08625 moles of OH minus. And we don't care about the rest of this problem here. Because we did what?
Overwhelmed the buffer.
We exceeded the buffering capacity of our buffer. Okay, so after the buffer canceled out as much as it possibly could, this was the leftover. So all I need to do is take the negative log of this value. And that'll give me my POH. So negative log, close parentheses, equals. And so I get 1.06. So my pH is actually equal to 12.94.
So what that 0.08 number, didn't that end up being negative?
No, because you have to think about what we're doing here. This is the amount of weak acid that's in the solution, and this is the amount of base that was added to the solution, and this number is the leftover base that wasn't reacted with.
Okay, but
Sure, stop. I know you do the subtraction, you get a negative number, but there's not negative stuff there, right? You have
so
to.
what I'm saying is that you just, even if you get a negative integer, you just take the negative out and just use the
Well,
number.
what happened?
We reacted the base with the acid.
So I had some of this stuff, and I threw in some of this stuff, but this stuff was much bigger, so I have leftover this stuff. So it doesn't really matter. All I need to know is how much leftover stuff there was.
Okay.
Basically, we're saying you have to understand what the answer is. So if this comes out to be negative 0.08625, that doesn't mean you have a negative amount of the weak acid. It means this is the leftover addition. In this case, the addition is lithium hydroxide.
So then you just don't do the ice portion of the
No, you need to do the ice so you can figure out how much is left over.
No, I know, but I mean on the right side of the ice problem.
It doesn't matter. None of the weak acid stuff is important because what you have is leftover strong base. So will it affect it? Yes. Will it affect it in, well, what decimal place is it going to affect it in? It's going to affect it in the, what is this, lactic acid, right? In the 4th decimal place. So we don't care because this thing that we're doing is, there's only 2 decimal places here. Okay, questions? Anybody?
Mm,
I think the only thing we didn't talk about actually was this page, and I just threw this in here because it seemed like I should put this in here. So
Yeah.
in case anybody forgot how to name acids, specifically polyatomic ion acids. Anybody any questions about this page?
I always have trouble memorizing chemistry stuff. I'd probably just need to go over it again.
Okay. What do we? Spring. But we're supposed to have the exam Thursday.
Oh.
That's cool. The next set of notes is super short, actually. No, that's wrong. Oh wait, I don't want this. I need it in here. Otherwise it doesn't draw well. Control V. Okay. So we've sort of had a discussion about part of this already, that the word insoluble, instead of being a go no go, it's more of a gray area. It's relative to the solution or the substance that we're talking about. And so when we say it's not soluble, we just mean that most of it isn't insoluble. That a small amount of it, at least for most substances, will still dissolve. Table salt, it all dissolves. But something like lead 2 sulfate, it's mostly not dissolved, and there's a tiny bit of it that does dissolve, but not very much. And we talked about the KSP symbol being solubility product. We talked about that at the end of last quarter. So if I'm looking at something like solid silver chloride, and silver chloride was what people determined to determine if there's any table salt in water. Let me let Jeff in. So even though it's that rule says silvers are insoluble, there's actual value for that. And I don't know why there's quotations around this. So the actual KSP for this is times 10 to the negative 10th. So what's that mean for you? Well, it ends up meaning that 0.0000018. So some of it is dissolved, just not very much. So we'd have that much silver and that much chloride. Is that important? What do you guys think?
No,
No?
because there's not a lot of it.
Anybody else?
I mean, I guess it is because there's stuff in the water now, but
Yeah. What it ends up being is it's definitely there. And so if it was something like mercury, even if it had a small KSP, mercury isn't something that just like kills you immediately. I mean, people were drinking straight mercury for years.
oh yeah, I remember that.
But if you have it accumulating inside of your body, because your body doesn't have a good mechanism for getting rid of it, because it's not expecting to have to get rid of it, it builds up and then ends up causing long-term diseases that you can't end up fixing them after you've gotten a certain amount.
What was that one unit we used last term when talking about super small amounts of something in water?
Parts per billion.
Oh yeah, parts per billion and parts per million.
That was actually fall term.
That was fall term?
Yeah.
For some reason I remember it being last term.
It's all blending together.
Yeah.
Oh, maybe I'm wrong. Maybe it was last term. See, it's all blending together. Okay, so with table salt though, the value is 36. So what that's telling you is the numerator for which controls this is a larger number than the denominator. So let's just write down what. So if I've got this reaction right here, what should this look like? KSP is equal to, and then I've got sodium ion concentration divided by chloride ion concentration. And down here, I would put NaCl. Are we okay with that?
That's from the last set of notes, right?
Yeah, I'm asking, are we okay with that? No, we're not okay with this. Why are we not okay with putting that there?
Because then it would just cancel out.
Nope.
Because
It
What-
fully associates in the water, correct?
Not necessarily. We're saying that it's a range. It's relative. What's this purple thing I've drawn on the screen?
that means concentration.
More specific?
Concentration of a substance.
It means molarity.
Oh.
It means mole per liter. Okay, so I can give you a mole per liter of sodium dissolved in something, and I could give you a mole per liter for chloride dissolved in something, but can you give me a mole per liter of NaCl solid? What's
No.
the concentration of solid table salt?
Concentrated.
100%, right?
Yeah, it's just table salt.
So I can't put that down there. So we end up losing it, which is why this right here doesn't have silver chloride in the denominator of the KSP. And this KSP doesn't have table salt in the denominator. And the KW for water is just H plus and OH minus. And the water molecule isn't written there because what's the molarity of water in water? So what stuff am I allowed to put inside this little brackety thing?
Ions?
Okay, so absolutely I can put aqueous substances. What else? I can also put gases in there,
Can you put liquids? in
but I
there?
can't put solids and I can't put liquids in there. We just said water's a liquid, right?
Yeah, but I'm saying like water plus a different liquid.
Well, if I write this, what am I talking about?
I can't see the screen. It's
If I write this, what am I talking about?
the concentration of water in molarity.
Which I can't write.
Yeah.
So
Okay.
that's why water isn't going to be written there. So no pure liquids and no solids are going to be written there because there aren't concentrations for them. The concentration of, so to think about it like this, I've got a container. It's got ions in it, and it's got this little pile of, say, table salt here at the bottom. What's the concentration of that table salt?
100%.
Well, what if some of it dissolves and turns into ions? And I'm left with less of the stuff. What's the concentration?
It'll still be 100%, but now the water is less concentrated.
More concentrated.
The water has a higher concentration of NaCl ions.
But the NaCl solid is still 100% concentrated, so it's not affected. All right, so in the, I wonder what these, why do these keep showing up in here? Must have been a weird transfer over. Okay, so if we're going to use the same process for calculating concentrations of ions for KSP as we used with determining the pH of water by calculating out the H plus or the OH minus concentration. So I know that when a silver chloride separates, I get one silver ion and one chloride ion. So then I don't know what X is, but I can assume that they're the same value, so it can become X squared, and we can roll through this whole process. So in this case, I know the concentration of the silver chloride is of the silver and the chloride in the water is 1.3 times 10 to the negative fifth. Okay? We're all right with that?
Yes.
So the cool thing about this is we didn't talk about the volume of the solution. Okay?
Okay.
Nowhere in here is solution volume mentioned. So what you should be asking me, so what you're saying is, if I've got a 5-liter container and a 1-liter container, and I throw silver chloride in it, those two containers are going to be at the same concentration? The answer to that is yes.
Yes.
Why?
Because it's the same substance that you're putting in each container.
Yeah, but concentration is moles divided by liters. And the liters is 5 times more on the other one.
Yeah, but are you putting in the same amount of, like...
Exactly the same amount of silver chloride.
Yeah, so it would be, because you're not filling the container to 5 liters unless you add water.
No, I'm saying I'm adding, it's 5 liters of solution. So
Okay.
this one's only filled to here, and this one's filled up here, and both of these solutions, concentrations for silver and chloride, are that value.
Okay, so you have a liquid in a bottle, and you have 2 containers. One is 1 and one is 5. And you fill them both to the top, is what you're saying.
Sure.
They come from the same bottle.
Yeah.
So they would be the same concentration because they're from the same bottle.
No. Let's start this over. Is that not showing it? So I've got a 5-liter container and I got a 1-liter container. I fill them both up. Then I add the same amount of silver chloride to both solutions. And what I'm saying is both of them have a concentration for silver of this. Can somebody tell me why?
Are you filling them both with water?
Yes.
And
Yeah,
so
it's
that's
moles per
solid.
liter. They're both moles per liter.
And that's solid silver chloride?
That's solid silver chloride.
If that's solid silver chloride, then wouldn't it just be 100? Never mind.
No, we're not talking about the concentration of the silver. We're talking about of silver chloride. We're talking about the concentration of the silver ion. So the silver chloride solid, some of it turns into silver ion and chloride ion. And this is the concentration, no matter the size of the container. I don't know what you mean by concentration is proportional, because in this case, it's not proportional, right? I've got the same concentration in 2 different size containers.
Yeah, if concentration was proportional, the bigger one would be less concentrated.
Anybody? The concentration
Because
is the same because it's a solid. It's still a solid. So this container over here got to 1.3 times 10 to the negative fifth concentrate a lot faster than this container here. But this container is eventually going to get there. As long as there's some solid silver chloride down here, it's going to keep dumping silver ions into the solution until what happens? Until it
gets to that
reaches
specific-
that concentration. So we could have a swimming pool filled with pure water, and I throw in 5 kilograms of silver chloride. The concentration of silver in that swimming pool is going to be 1.3 times 10 to the negative fifth, as long as there's still a little bit of solid silver chloride in the pool. It'll take a lot longer, but it'll happen. So, anybody want to tell me why that's kind of cool?
Because silver isn't supposed to dissolve in water.
No, that's not why it's cool. Because it's science. Yeah. Because you
Okay,
can
but
look
why-
you can look at the KSP value for an insoluble substance and throw it into a container and know what concentration it's going to be. No matter what, it's going to be that concentration. Doesn't matter the size of the container. You know exactly what the concentration is going to be, no matter what. Not impressive? Nah.
Could
You
you
guys-
use that to like gauge other concentrations if that's like,
Hell yes. That's exactly what we do. I know the silver concentration is going to be this, and I can start adding stuff to it. And then I can gauge those concentrations based off of what the silver is doing.
Okay, but why does it only go to that specific number?
Because that's the KSP for silver chloride at that
Okay,
temperature.
okay, but why?
because nature says so?
Why is your name?
Listen,
Why is your last name
I don't-
Rutherford? Because it is.
I don't know.
Because that's the way silver chloride separates in water. That's its proportionality.
So what if you like put a little tiny bit of silver chloride in like a 5?
Then it won't make it.
It won't do anything.
It won't get up to 1.3 times 10 to the negative fifth.
So some parts of it will dissolve, but
It'll
there's
all
not enough to
dissolve.
get to the-
It would all dissolve. If you put a teeny tiny bit in there, it would basically almost all dissolve. So if you
Okay.
threw a little bit of it into, the ocean, the stuff's going to dissolve.
Yeah. So solubility rules, right?
Yeah.
Dictate that silver can't dissolve. in
Right.
water.
Yeah. Yep. But it will. Because
I hate when you do this.
it's actually relative.
Okay. Okay.
Well, I can't tell you everything at the same time or your head would explode.
I know, but it's just really frustrating, like knowing something and then realizing that that thing is completely wrong and I'm dumb. You know?
Nobody's
So what you're
dumb.
saying is, as long as you have a big enough piece of silver chloride, this will happen.
As long as your piece doesn't fully dissolve, you will reach this concentration.
Okay.
Yes.
So what you didn't tell us in the beginning was those two pieces of silver are different sizes.
No, I didn't say that they were. They could be the same size, just as long as the one in the 5 liter one doesn't fully dissolve.
That's true. Okay, I get that.
Okay, so this calculation is pretty easy because it's a 1-to-1 ratio, and I know what I can just put it to x squared. But what if we're talking about lead chloride? So lead 2 chloride specifically. So that means I've got 2 chlorines and I've got 1 lead. So when this dissolves, I end up with 1 lead 2 ion and I end up with 2 chloride ions, right? 1 of those and 2 of those. So I know I'm going to have twice as much chlorine as I do lead, but the math becomes a little bit more difficult, right? Not a lot more difficult, but you have to think about that my expression has a square right here, right? But I do know that every lead that I'm going to get off of this, I'm going to end up having 2 chlorides, right? So then I could call this X and I could call this 2X. We okay with that? Like this is when you're
Yes.
really using like Math 111 stuff. So
Okay.
So now I've got, maybe we'll use a smaller one here. Now I've got this 2X here and this X, but I still have the 2X squared.
What?
This is my KSP for lead 2 chloride. Okay. So I've got X times 2X squared equals the KSP. So I can distribute the X across, or the square across the 2 and the X. So I end up with 4X squared. Does anybody have a problem with me going from 2X squared to 4X squared?
Wouldn't it just be 4x?
No, no.
Because Q. Oh,
no.
no.
2X
No.
times 2X is 4X squared.
I
Alright?
forgot about the x. I just remembered the 2. Okay, it's fine.
So nobody has a problem with me turning that into 4X squared, right?
No.
All of you people who have taken math. All right, so then I can take this X here and I can throw it over into that X, and now we come up with X to the third, right?
Okay.
Because what we have here is X to the first times 4X squared, right? So then I just add these guys up and we end up with 4X to the third. Good? 4X to the third is still equal. We haven't touched the KSP in any way. And so what do? Well, I divide both sides by 4. And then I cube root both sides. Who knows how to cube root on their calculator?
Don't you have to go to math?
No,
Yeah, you do.
you
Well,
don't.
I do.
You don't. Does anybody know how to make it easy? Just do an exponent. You are correct. So what's the exponent version of a square root?
Oh,
1/2. So Colleen is showing you that the cube root of the exponent form of cube root is 1/3. So you can take something like I don't know, I'll just make a number up, 125. I don't know, can you see that? Oh wait, let me do this.
thank you.
Can you see that? Is it
Yeah.
backwards for you?
No, it's the same way.
Huh, why is it backwards for me?
Because it's not backwards for us.
That doesn't make any sense.
It makes a lot of sense actually.
Okay. So then it just, why are you not? Then it's just 5, right?
Okay. So if you were to, if you did the cube root of 125 without the exponent, it would just be the same number.
Yeah, so see how what the calculator did, the 125 there, and it shows the exponent form of 1/3? Why are you holding I don't know what that is, a lion? Have you been
Me?
holding that the entire class?
Me?
No, not you. Are you holding a lion or anything?
Gage?
No.
Oh
Ethan.
no, that's a stuffed animal.
Yeah, thanks. I get that.
Pokemon?
He's had it the whole time, yes.
I know what it is. He's told me what it is, but I forgot.
Okay,
Isn't it
so
hard?
pulling
Oh.
an Ethan, we're moving on here. And so I'm taking the cube root of the 4 times 10 to the negative 6, then I end up with 0.016 molar. So what is this 0.016 molar? What is this telling me?
There's 0.016 moles per liter.
You gotta swap back to your screen as well.
Oh,
Yeah.
crap. Thanks. I was drawing and
I'm guessing right here. Okay.
So this concentration is the lead's concentration. What's the concentration of the chloride?
0.016 moles per liter.
Times 2, because there's twice as many of them.
Oh, okay.
right? So we knew it was X, but in this case, the X is lead, and it's 2X for the chlorine because there's twice as many of them.
Okay. So the concentration is the same number, but then
No, the X is the same number.
Wouldn't it be divided by 2 since it's 1 pp is equal to 2 CLs? Or is that just not right?
No, we solve for X.
Yeah.
And we said X was the
Okay.
concentration. This X right here is the concentration of the lead. And then we compared the concentration of the lead to the chlorine, but we said it was twice as much, so that's how we got the 4X squared.
Okay.
And this little paragraph that's bolded is talking about what we just talked about with the solution concentration not changing basis off of volume. Okay. So forcing the solid state. That's what we're going to talk about a little bit. So let's say that you've got some barium in your water and barium's toxic to people. How do you get rid of the barium?
You turn it into solid barium with a different attached to something.
Yeah, the ion is toxic, but the ion is also not soluble in lots of things. So if you just used, there shouldn't be a 2 right here. I'm not sure where there's a, oh, it needs to be out here. My bad. So if we added fluorine to the water, it would react with that and form insoluble barium fluoride. Or if I had barium ion and I threw in magnesium sulfate, solid, well, that's fully soluble. So we'd end up with barium ions, magnesium ions. That's horrible. And sulfate ions. And barium and sulfate together make BaSO4, which is a solid. So if you're running around with some Epsom salt, you could dump that into the water before you drink it, and almost all of the metals that will kill you over time will be precipitated out. And you should be able to see it almost instantly if you were to take the barium sulfate. Instead of throwing the solid stuff in, you had a container that had dissolved barium or magnesium sulfate in it and dribbled magnesium sulfate into the water. You should be able to see the precipitate form immediately, or almost immediately.
Magnesium?
What about magnesium?
Wouldn't it be harmful?
What?
The magnesium, would it be harmful to humans if they drank it? Because there's still magnesium ions in the water. Oh, it's a mineral. Okay. I don't know. I don't have all this stuff memorized.
Like magnesium additive? You've never heard of anything like that?
Oh, yeah, I guess.
Okay, so you do know. All right.
I mean, now I do.
I thought there was an image here. Let me flip back over there. Oh, that's what the problem is. None of this stuff came over formatted correctly. Wonder why. There is an image here. Stupid. You would think that a Microsoft product could talk to a Microsoft product.
Mm.
What do you... Really? Sorry, let me paint. Control V. God, that's tiny. Control A, Control C, Control V. Okay, well, that worked. I wonder why it wouldn't just let me straight away copy that. Okay, Lewis base equilibria. So we saw this, and I mean we've basically already talked about this stuff. So it's just how is this Lewis base equilibria affected by, or how is the equilibrium affected by the fact that these things are Lewis bases or acids. It's really not a big deal. It's the fact that this lone pair of electrons, and so in this case, the nitrogen's acting like what?
A proton acceptor?
Lewis.
it's
We're talking about Lewis. We're not talking about Bronsted Lowry.
It's acting like an acid.
Okay.
And it takes the H.
Okay. Does that sound right?
It's acting like an base.
Are everyone's mics broken? Are we just tired? You're like,
I'm
want to go
trying.
outside?
I'm the only one with a mic on.
I can fix that. All right, so now almost everybody's mics are on. Somebody says now everybody's mics are on. Yeah, somebody speak.
Fantastic.
So the ammonium or the
You can't see the screen anywhere, Rob.
I know. Just be thankful I can't unmute all of your video.
You can't? I thought you could.
I can allow you to start your video, but I can't turn your webcam on because that would be weird.
that would be bad.
I can turn your mic on, so know that. Your instructor can turn your microphone on unless you're holding full control over it, which you kind of need to know what you're doing for that to happen within Zoom. Dogs. Whose dog?
That's my dog. Can I mute myself?
Yeah, I can't stop you from muting yourself. I can only, again, unmute you.
Just answer the question first.
But yeah,
So the
to mute,
NH3
I'm just going to keep unmuting you if you don't answer the question.
So
what-
the NH3.
The ammonia is doing what?
It's stealing an H. It's taking an H.
Yeah, that's not what Lewis would say.
Lewis.
Donating electrons?
It's donating electrons. So what does that make Lewis?
Lewis?
Sorry, what does that make the ammonia as far as Lewis is concerned?
A base.
It's a base, because that's the definition of a Lewis base, donating electrons. Specifically, if you have a substance that donates both electrons, which nitrogens like to do, the name for that is either a coordinate bond or a dative bond. And we have that right here. And it's technically a covalent bond because that's a terrible color.
We can't see.
Supposed to know when I want to flop back and forth. So co-coordinate is right here, dative is here, and it's a covalent bond because this is hydrogen and this is nitrogen, and their electronegativities are similar enough that we'll call it a coordinate covalent bond.
So, what does the coordinate mean?
It means that this one thing, this nitrogen here, provided both of the electrons to form the bond.
Okay, and then
The hydrogen came empty-handed.
and then does the dative correspond to the H because it doesn't.
No, these mean the same thing. It's two words for the
Oh.
same thing.
Oh, okay. But so the H isn't providing anything, is what you're saying?
Yeah, the H shows up as an H plus. So tell me, what does an H plus consist of?
One positive.
That's it. It only has a proton. There's no neutrons, there's no electrons, so it doesn't have any electrons to form a bond. But the nitrogen was nice enough to donate these two electrons so a bond could be formed. So that bond that's formed is a dative or coordinate bond.
What happens to the extra electron?
There aren't any extra electrons.
But there's one proton, and there's two electrons.
What are you talking about? You mean, why did this become positively charged?
No, I'm talking about, you said that when it attaches to the ammonium, it,
The nitrogen provides both electrons.
yeah.
Well, a covalent bond is composed of 2 electrons.
Oh,
So there's 2 electrons. So
okay.
usually when we're talking about a covalent bond, I've got a hydrogen that shows up with 1 electron, and I've got a carbon that's got another electron, and the covalent bond is formed because each of them donate. So what I'm
Oh,
saying
right.
is, in this case, if it's a dative or coordinate bond, that bond's formed. One atom provides both electrons for the 2 electrons.
Right, this is first term stuff.
Maybe. Yeah, some of it for sure. Huh. So these things aren't showing up. So, all right, that's frustrating. I'm gonna have to go back over this. All right, so we've got just a couple. Yeah, none of that stuff. Were there pictures up here that I was missing? No, it was just not formatting it right. Okay. So let's talk about ion complexes. So these are some pretty important ion complexes. And so if you want a yellowy orange or a purple or a red color or a green color, you'll do something with metals, and it forms these interesting with they're called ion complexes. So if I've got a cobalt and it's in an ammonia solution, you'll end up making this really cool orange color, which can be used for a dye.
So can it be used in paints too?
Or be used in paints. Yes. So most of the really bright, vibrant colors are formed by these coordinate complexes with a metal, and it's going to be a transition metal, and around that are other ions, and those things are usually called ligands. And so in this case, the ligand is ammonia. And so in the next one, how does the first and the second one change?
The orange and the purple one?
Yeah,
There's one chlorine.
there's 1 chlorine. So I swap out 1 ammonia for 1 chlorine, and the color switches from yellow, orange to purple.
Hmm.
But if instead I move on and I take, basically it turns out to be a hydronium ion, and attach it to there in that same spot where the chlorine was, or where one of the ammonias was, it changes to a red. And if I change it to 2 chlorines instead of 1 chlorine, bumping off ammonias, then I get this green. So you can take these metals and put them in different solutions to get these different complexes to give you different colors.
So if you just add more chlorine, then it gets to that green color?
Correct. Then the equilibrium will switch, and then you'll end up adding chlorines that bump ammonias off, and I get a different color. So if you're someone who's making paints, you're going to have cobalt on hand, and you're going to have ammonia on hand, and you're going to have soluble chlorides on hand, so you can cause these different substances to create different colors. In our lab, we have green stuff. Is there chlorine? Chlorine. There isn't any chlorine in your lab kit. There's certainly some chloride. Chlorine. There's no canisters of gas in your kit, so don't worry about that.
I think she's talking about the universal indicators.
Yeah, I'm not sure. The universal indicators vary. So that's is it a 1 to 4 or
Yeah.
1 to 7 and a 4 to 10? Yeah, I think it's a 1 to 7 and a 4 to 10. So those substances have these complexes in them, and then depending on what the pH is, they'll change to a particular color.
So if you were to give us a chemical with like an orange color, then the ion complexes would be the ones giving it that color?
This could be, but there are other ones that give orange color that don't have these, that have this cobalt with these ligands. Just showing you that I can take a cobalt and change the things that it's in a complex with, and you get these different colors.
And then those can be used for dye, which can be used for coloring drinks and stuff.
Drinks? No, not drinks. Not these.
I'm just like, you know how there's like blue dye in like Gatorade?
Sure, yeah. It doesn't have this in it though.
Okay.
And they've been trying to make So have I'm assuming that most of you have heard that people want to remove particular dyes, food colorings from different foods.
Yeah, some people are really allergic to red dyes.
So it depends on the dye and depends on the concentrations, but some of those things can be either they'll have an allergic reaction to it or people just think it's bad for them and so they don't want that in there. So what's been happening is like 2 or 3 years ago, Fruit Loops switched. So all of the dyes that we've been using in the US and the world for the last 50 plus years, they switched them over to different ones that are plant-based.
Oh,
So I don't know if you like Fruit Loops or not, but the Fruit Loops themselves have actually changed colors.
well, it didn't really change the taste. At least I didn't
Well,
notice
they
the
they don't
taste.
have flavor; they just have color. So
That's okay.
they're not as bright as they were before. They're more
Yeah, they're
pastel-y.
duller now.
They're definitely duller. And so is that something that
It,
bothers people?
it's
Is
just
the
cereal.
right? I mean, but some people think that because it's a different color now, it's not as fun for the kids, so maybe I can't get them to eat this cereal. Like,
Is that
okay,
why Fruity Pebbles is so colorful?
yep,
Because fruit, like,
they haven't switched.
okay. Also, don't feed your children cereal. Maybe
I guess it depends on the cereal.
some cereal is okay, but like in general,
In general, it's
is
just
bad.
carbohydrates with sugar on them.
Yeah, exactly. Thank you.
Change is bad, and I'm angry over the hue of my cereal.
She's
Yeah,
What about
angry.
Wheaties? What about Wheaties?
that is a serious first world problem,
Ew.
right? Angry over the hue of my cereal.
She's
What
angry.
about the Sour Patch Kids cereal?
No, we're not gonna talk about Sour Patch Kids cereal. We are moving on.
That can't possibly be a thing.
It's a thing. It's a real thing, and it's gross.
That's disgusting.
It's gross.
Okay, so here you can see a bunch of different ions with different colors, and sometimes the covalent compounds make colors and sometimes they don't. So you can see the zinc and the manganese, and at least manganese 2, are colorless. Well, maybe the manganese is
Manganese is
slightly
pinky.
pinky. Okay. The cobalt and the 2 different forms of iron, and then the chromium and our copper there at the end, and then the nickel. So it totally depends on the solution. These guys are just strictly dissolved in water. But if you change the pH by adding ammonias or removing ammonias or adding acids to it, you could get these colors to be modified. And so, since most people don't eat paint, they'll add these to there. But what's the
Oh.
problem with eating paint
um,
besides the fact that it could kill you?
paint.
Well, who
I
eats paint?
don't-
Kids eat paint, right?
Oh,
Kids actually eat paint. And it's not that, and he is correct, lead-based paint chips are sweet. But more importantly, what ends up happening is if you're in an old home that's got very old paint in it, and it's lead-based paint, then that paint will flake off the wall. When you rub against it, it turns into a dust. That dust goes to the ground, and if you're a 1-year-old, you're crawling around on the ground, and then obviously you're going to put your hand in your mouth, and now you just
Yeah.
put lead in your body. So that's the problem with lead-based paint. Why did people put lead in paint?
because it looks nice.
Because it's very vibrant.
Yeah, but it takes a very thin layer and it stays forever.
Well, kind of, but
Almost
It-
until it
it
flakes
turns
off and
into
it goes
dust.
into your child's body.
yeah. So
Oh,
Who-
what if we
who else is susceptible to this paint eating thing?
old people? No, dogs, animals.
Yeah, not. I mean, a little bit maybe. We already had children.
Not animals?
How about painters?
Oh, yeah.
People who paint
But,
gets on their hands. What are we are? We're gonna talk more about Radium Girls. I wanted to see
Yeah.
that, but it got canceled.
It was so good. I'm so sorry you didn't see it. And they didn't even get to record it.
That's terrible.
Which is, yeah. That was really cool.
So yeah, that is a horrible story. But the issue is painters will lick their brush to make a fine line.
not even that. Whenever you're painting, it just gets messy, and
Yeah, sure.
you end up getting paint in your everything.
So they've exhumed some famous painters' bodies and found that the inside of their coffins have lead in them and various forms of chromium and whatnot that probably didn't help help them along in life. Certainly could move them into a disease that killed them. So now
Are these-
lead's not allowable for paint.
Are these the only colors that we can make, or are there more?
No, I just said that you can take these guys and you can vary them based off of what the pH of the solution is.
Okay, so
And-
you can
and
just
you
get
can-
like a full rainbow.
Yeah, well, that's pretty close, right? Red, orange, yellow, green,
We're
blue,
missing
violet. You
purple.
got a whole rainbow there. There's Roy
Is
G. Biv.
Chromium purple?
Yeah,
Oh, I thought it was just really dark blue.
that's
Yeah, I guess.
really dark purple, almost black. So yeah, these things get added to paint, and so when you're at like Home Depot, when you're the only person in the store and you're buying paint, and they're tinting it for you, they're throwing these kinds of things in there.
Nice.
All you need is red, yellow, and blue.
I mean, she's
Yeah,
right.
but you have to be good at mixing
Well, you
paint,
also need white. But that's it.
and you need more of it if you're going to mix it like that.
Yeah.
Okay, so you can scroll down here, and if you're buying black paint, what is it that they shove in the paint?
Urban.
Carbon,
Well,
yeah.
specifically, what is it? It's
Charcoal.
soot, charcoal. Yeah, they're literally grinding up charcoal into a very fine powder and adding it to the paint. That's where the black comes from. When you're getting this color blue, you're having a cobalt iron complex. Sorry, tin complex, cobalt tin complex. You want green, here's some chromium. You want a purple, here's a cobalt. Cadmium gives you this nice orange. This is the most important paint color of all.
Titanium white.
This titanium dioxide is produced more than anything else as far as paints are concerned. And it's sometime in the near future, well, we're doing it now, producing it in nano quantities and adhering it to the surface of windows. Now that might sound bad, but if it's a nano thickness, you can still see through the
Oh.
window. So why would you paint the window with titanium oxide?
And make it strong.
Stronger, not insulation. What'd you say, Sheen?
UV protection?
That it actually does protect against UV. Anything else?
Well, you said no on stronger.
Correct.
Okay.
Stuff doesn't stick to it,
Yeah, I was about to say, isn't it
Oh,
cleaning?
so the window stays cleaner longer.
Aren't
nice.
they also adding that to concrete to make it so the concrete stays like nice and pristine colored?
When the concrete goes down, you will be like, wow, that concrete's really fresh, and it's because they basically threw the additive for white paint in it, so it looks more bright. It pops more, and
Nice.
concrete itself is a mixture of whatever the heck you want to put in with the cement. So it doesn't matter that I'm throwing in these titanium dioxide flakes, which are basically rusted titanium. So nothing's going to happen to it. It's not reactive in any way. So you can see other versions of this antimony version, which isn't quite as good because it's antimony is more toxic. But how about zinc oxide? Where have you seen that before? Sunscreen, yeah. Like
Oh.
pictures of like lifeguards with white noses. It's zinc oxide on their nose. In that sunscreen stuff. And then there's several different versions of blue. Why do you think that one's called Prussian blue?
Prussian. Because it's from Prussia, or it was the color was.
Prussia, that area was figured this color out and was exporting it. Yeah.
Nice.
So then we've got other ones, and you can look at that first blue complex, that ultramarine blue. Look how much
Oh,
stuff
that's
is
such a
in
pretty
it.
color. Oh my god.
Isn't Prussian blue like really dangerous to make though?
Yeah, what do you see what's in the Prussian blue?
Cyanide?
Cyanide. Yeah. So you have to have something like sodium cyanide or cyanic acid that you're going to add to to iron to get this complex. So you've got a solubilized version of cyanide floating around in your laboratory or your building where you're putting it together.
I'm thinking of like all the times I used acrylic paint and like licking my paintbrush, and I'm just regretting all of my decisions
Yeah,
because
you're too young to have had access to bad paint.
yeah, no, it's like high quality paint, so I guess you're right. Okay.
High quality doesn't mean it's not dangerous, but you
Like, use
actually
all these
you
colors.
can't just buy high quality paint. Sorry, you can't just buy lead-based paint at like
Yeah.
Joann's Fabric or at like Michael's. You just it's not there. You can purchase
So
it,
even
but it's hard to get your hands on.
so even though like you said ultramarine blue, it has cyanide, but even though I'm like licking paintbrushes,
No, I
with
didn't say
ultramarine-
that. I said Prussian blue has cyanide in it.
Oh, okay.
So Prussian blue isn't something that's sold in cans of paint anymore.
Yeah, okay. 'Cause
They've
I use ultramarine
substituted
blue
the
all
cobalt blue and the ultramarine blue for it because it's pretty close to the same color and it doesn't
Yeah.
kill people.
time. Okay.
So we've got the verdant green with some chromium in it, and we've got the cadmium green. Both those things are not great, but they're the ionic forms that aren't as dangerous as their other forms of +6.
Isn't cadmium yellow pretty dangerous? I just remember my art teacher saying something about like
Yeah,
being really careful with the cadmium yellow.
the cadmium yellow and the lead chromate
Cadmium
yellow are
yellow.
dangerous. So the one that people tend to use these days is that zinc yellow, which doesn't pop
Okay.
as much as the lead or the cadmium, but
Yeah, cadmium yellow is a beautiful color, but I just remember being scared about it all the time.
yeah. And then you've got, I mean, if you look at this, you'll see there's a lot of cadmium floating around, there's a lot of chromium floating around, and there's some lead floating around and cobalt. So those transition metals are the ones that give us most of our colors. And the colors themselves are produced again by these complexes in the solution. So if we were, how do I make this smaller? If we were live, we would do this lab. This is like, there's like 5 or 6 chemistry labs that if you take a full year of Gen Chem, like everyone will do it. But we're not doing this because I can't have you do this at your house. So it's actually super fun, at least, you know, coming from a chemist. But you have all of these options, all of these different ions, and I would take maybe 3 of them and put them in a container for you and say, go tell me what 3 of these I pick. So I don't know how many are there. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 26 different ions here. And I could put 2, 3, 4 of them in a container and say, tell me what's in here and what's not in here. And so you have to go through this process of figuring out what's actually in the container. So if you add 6 molar hydrochloric acid in it, you're going to get 3 of these possible, what do we say, 26 to precipitate out. So if you get a precipitate, you know it's one of these 3. And based off of what the color is, because all 3 of these have different colors, you know actually which one was there. So immediately you could identify if you had silver, lead 1 or lead 2, silver or mercury 1 or lead 2 in your solution. And then everything else doesn't care about 6 molar hydrochloric acid. So then you'd move on to the next step and add some hydrogen sulfate and some hydrochloric acid and you get different precipitates or nothing. And then you'd add sodium hydroxide and you get different precipitates or nothing. And then you'd add some ammonia, different precipitates or nothing. And then when you're done, if there's nothing, if those things didn't precipitate out, why would you be left with these 4 things? What do you know about these 4 ions? I don't know why this one's written twice, but whatever. These 3 ions.
They are soluble in water
They're soluble in everything, right?
and everything.
So they are. You weren't going to be able to add anything to them to get them to precipitate out. But do you remember
Do you remember?
from the first quarter we did a lab about, was this a chemical reaction or was this a physical process? and you took some table salt and you dissolved it, then you boiled the water off, and then you put it into the
Mhm.
flame,
Yeah,
what color did you
kind
get?
of. I remember putting something in a flame and then it turning like black super quick.
Yeah, no.
But that's all I remember.
Anybody
Probably
else?
the one.
It turned yellow.
It turned very bright yellow, like the color of a regular flame. So if you did that at the end here, you could do a flame test on it and realize that you had sodium if it was yellow. If it came up red, then you knew you had potassium, and ammonia doesn't give a color, but you can
What was the
check
flame that
pH.
ended up? What was the flame that ended up being green?
We didn't do one like that.
We didn't.
No, that wasn't this
I
class.
have the same. I had the same kind of lab in high school where we did flames, and one of the flames was green.
Yeah, you would take those different metal ions and then put them into the flame, and you would get different colors. And we're going to talk about that when we get to the radiation stuff. And
Maybe copper. I don't know.
that's the end of that set of notes.
Oh wow, that was actually really short.
And this is going to be on the exam on Thursday, correct?
That's correct.
So are we having?
I'll throw out a
class-
homework, and so really most of the exam is, almost all of the exam is acid-based stuff, and then there'll just be a tiny bit of this equilibria stuff on it.
So are we having class, or is it just going to be an exam?
I'm gonna sit here in Zoom, and I'm gonna watch Moodle, and you guys are going to. I will know as soon as you get into the exam, and I will know as soon as you submit the exam. And it's gonna close before right as class ends, so you won't be able to download or look at it or submit it if it's past the time.
So why are you going to be sitting in Zoom?
So I can make sure people are doing it.
Oh.
And if anybody has any questions, because I mean, I'm writing all of this stuff now. There's certainly I mean, you know my propensity to make typos. There's certainly a possibility, and so you could pop on Zoom and be like, "Hey, this question, is this a typo?" And I could tell you yay or nay.
Okay.
We don't have to be in the Zoom meeting, do we?
You do not have to be in the Zoom meeting, but
Okay.
that's a thing that some instructors are going to do. And
That you'll have to be in the Zoom meeting while you.
with your camera on,
I mean,
No.
that's fair.
and in an angle that will show you and your computer and your desk.
See, I don't know if I can do all of that. I mean, I get why. But
You could just put it on that shelf right there next to you on your left. Just set it right
So
there.
they just want but I don't have a computer. I use my phone.
You wouldn't be able to take the nursing exams on your phone.
Well, luckily, I'm not going to be a nurse.
So I'm just saying that some of you might encounter that where someone's going to
Yeah.
require, because we went in and checked. We actually as soon as we found out we were closing campus, we checked on some software where people were going to proctor exams, and they were ridiculous. They were like $75 per student per exam. So that was not going to happen. So what we came up with is you just set your webcam in a spot like adjacent to you where you can see the person and you can see and hear everything that's going on. So it's not like somebody's going to be in the background on another computer yelling the answers out to you, because you would immediately know. Somebody wanted, well, what if we have two webcams, one facing from behind them and one in front of them? I'm like, it's getting
What
a
if
little
someone-
overkill.
What if someone like recorded them doing stuff and then like just put because you can have webcams where you just put a pre-recorded video over it. People do it a lot on like what is it called, Omegle, so that it looks like you're actually there doing stuff, but it's just a pre-recording. I mean, you got to be real high tech to probably do that, especially on Zoom, but I feel like it could happen.
I feel like if you're doing that, you should be doing some other class, right?
You should be
Should be
not
working for
going to
somebody.
college.
All right, so I'll end this. I'll throw homework up and finish writing the exam, and then I'll see you taking exams on Thursday.
40 questions, right?
Probably. It won't be 20,
You don't know.
and it won't be mistakenly giving you less than I expected. That won't happen again.
That was fun.
Questions? Anybody about anything? Whatever.
Is the exam gonna be mostly math?
Nope. No. And don't be freaked out when the question is different format than you've seen before.
Yeah.
Are they multiple choice or?
Some of them are. Some of them are calculations. Some of them are move
Questions.
boxes around and put them where they're supposed to be. I learned how to do that. I thought that was kind of fun.
Yeah, you're the only professor that I've seen with those type of exam questions. It's always like multiple choice, and everyone else, because they don't put too much effort into it. But yours are like bank questions and fill in the blank and multiple choice. I've never seen that many types of questions on any exam in Moodle.
Well, I don't want it to be boring.
Yeah.
The other option, we might actually try that live exam thing where you all have webcams on and we're the only person that can see you is me, but you're all taking your exam. Because I kind of need to see how it works. Yeah, Fatima, it's probably going to be about 40 questions. But at least you wouldn't have to take it on Moodle. You would just basically like, how would that work?
What? Yeah.
Sorry, I'm just like coming up with problems as I think about stuff. How many of you don't have a printer?
I do not.
So 1, 2, 3,
Printer's
4,
broken.
5.
I have a printer, but I don't really know how it works. So. Tips.
I'm
trying
sorry,
really
but
hard to
you
think of
need
what
to-
it makes me cry.
Printers do that for sure. Okay. All right. I'll figure something out. Only half a page? That's cool.
Maybe the inner workings of your printer is broken. You only have to take half the exam.
And you only get half the credit. See, it all works out.